Hiya, it's Mr. Baker here. Today we're going to be looking at momentum and impact forces. Okay, so today we're going to be looking at impact forces, and we're going to be looking at this question: why don't you hurt yourself when you land on a bouncy castle? Okay, well, it's probably pretty obvious, but let's do it anyway, shall we? Okay. Right, so we have looked in the last couple of lessons at momentum and the conservation of momentum, and today we're going to be looking at how momentum and force, and in fact how the change in momentum is linked to a force. So when a force is applied to an object, the object's velocity changes. This means that its momentum has also got to change. The change in momentum depends on the size of the force and the time for which it's applied. The relationship between this value is shown by an equation that is this. Now this is an important equation that you've got to be able to use. It's force equals the change in momentum divided by the time. Or another way of saying it is that force equals the rate of change of momentum. So momentum is measured in kilogram meters per second, time is measured in seconds, and force is measured in newtons. So if you look, so we've said that the force equals the change in momentum divided by the time. So if the change in momentum, so in other words, if the momentum before take away the momentum afterwards, if that's a big number, then the force is going to be big. If the time is very small, then the force is going to be big. If the time is very big, then the force is going to be small. So we're going to see how that equation is really, really important when we're looking at impact forces and design in cars and things like that over the rest of this lesson. So let's just go straight into doing a couple of example questions. So we've got Johnny Wilkinson there just about to kick a ball. A rugby ball of mass 0.5 kilograms is kicked from stationary to a velocity of 8 meters per second. The kicker's foot is in contact with the ball for 0.1 seconds. What force does the kicker use? So we've just said that our equation is force equals change in momentum divided by time. So let's go through this stage by stage. The change in momentum is going to be, so we've got the mass of the ball, which is 0.5 kilograms, times 8 meters per second, because we know the final velocity is going to be 8. The initial velocity was 0. It wasn't moving before he kicked it, but the mass was 0.5. So we've got 0.5 times 8, take away 0.5 times 0. The time that his foot was in contact with the ball was 0.1 seconds, so that goes down there. Now 0.5 times 0 is 0, so 0.5 times 8 is 4, so 4 divided by 0.1 is 40 newtons. So his foot provided a force of 40 newtons to that ball over the time period of 0.1 seconds because of that change in momentum. Let's look at another example. A tennis ball is rolled at a toy car of mass 0.1 kilograms. The car is moved with a velocity of 0.5 meters per second. If the ball and the car are in contact for 0.05 seconds, with what force is the tennis ball rolled? So here's our equation again. Force equals the change in momentum divided by time. You might want to pause the video, see if you can work through it and get the answer, and I'll go through it with you in just a couple of seconds. So if you want to do that, pause the video there. Have you paused it? Okay, well, let's see. So the change in momentum. So we know we're looking at the momentum afterwards, take away the momentum before. So the momentum after is going to be the velocity times the mass, or the mass times the velocity. So we've got the mass is 0.1 kilograms and the velocity is 0.5 meters per second. Before that, it wasn't moving, but it still had the same mass. The time that those two were in contact was 0.05 seconds, and so 0.1 times 0 is 0. So we have the momentum afterwards, which was 0.1 times 5. Sorry, 0.1 times 0.5 equals 0.05. Divide that by 0.05, and that equals 1 Newton. So have you tried that one? I hope you got that one okay. Hope that was all right. Let's move on. So we've said that this is really important in car design, and when we're looking at car crashes and things like that. So what happens if two cars travelling very quickly collide? Well, both cars come to a stop in a really short space of time. This means that the cars and their occupants experience a really large change in momentum very quickly. Why could this cause a very serious injury? So if you're going to have a very large momentum, change in momentum happening over a very short amount of time, then because of our equation, force equals the change in momentum divided by the change in time. So if you've got a large change in momentum divided by a small change in time, you're going to have a massive force. Okay, so a very large change in momentum in a short space of time means the car occupants will experience a very large force. So using this principle, how could you improve car safety of cars? Well, there's a number of things that cars have got as safety things in their cars, which we use this whole theory because of. So many modern car safety features work by increasing the amount of time taken for the person to decelerate in a collision. How does this reduce the risk of injury? So basically, in a car crash, there's not much that the car manufacturers can do about the speed that you're going to be driving, and so the momentum change that you're going to have if you crash. If you're moving along in your car at 30 miles an hour and you crash, the momentum is going to be the same no matter what car you're in. You're always going to have a momentum change of 30 miles per hour, so the speed times your mass going to the zero speed times your mass. So that change in momentum is always going to be the same. So you can't really do much about the change in momentum. And we know that the force equals the change in momentum divided by the time. So what we can do though is we can increase the time it takes for you to stop. So if you can increase the time it takes to stop, then you're going to decrease the force that you're going to feel. So having a longer deceleration means that the change in momentum occurs over a longer time and is therefore going to have a smaller force acting on the person. So there are three key features that car manufacturers use. We have seatbelts, airbags and crumple zones. So a seatbelt, when you stop suddenly and you're wearing a seatbelt, the seatbelt slightly extends, it slightly stretches, and so that the time that it takes you to stop is slightly extended. I mean, it also stops you from smacking your head into the thing in front of you, which is either the steering wheel or the seat or something like that. But the seatbelt stretches, and so you're decelerating over a longer time than you would normally, and so by increasing the time, you're decreasing the force. An airbag does a similar thing. If you have a crash, then the airbag will pop out of the steering wheel or other places in the car, and when your head hits into the airbag, it will slowly deflate, and so it will increase the time it takes for you to stop. Otherwise, you smack straight into the thing in front of you, and it would be over a very short amount of time, and there'd be a large force. And the third thing that cars have are things called crumple zones. So these are literally, when they're made, they have these little folds put into them pretty much, so that when a car hits into something, the metal of the car will kind of fold instead of just stopping straight away. So it used to be that cars used to be made of really hard metals, and when they hit into a wall, they didn't do anything, they just stopped, and the wall probably went and the car was probably fine afterwards. But the passengers inside, because the car didn't do anything, the passengers inside would stop very suddenly, and so the time over which that they stopped was very small, and so the force felt by them was very large. So now cars have these crumple zones, so when a car collides with something now, it will sort of fold up, it will crumple, and as it crumples, that increases the time for the crash, and if it increases the time for the crash, then it decreases the force that the passengers inside the car feel. Okay, so that's pretty much the lesson over for today. So we've been doing impact forces today. So these are the things you should be able to do. You should be able to describe the factors affecting impact forces, and you should be able to describe collisions in terms of forces and conservation momentum, and hopefully be able to calculate the force involved in an impact from the change in momentum over time. So back to our question that I posed you at the beginning of this lesson. Why don't you hurt yourself when you land on a bouncy castle? So a bouncy castle is just a castle made of air, isn't it? So it's got lots and lots of air, so if you bounce into it, if you hit into it, the material, instead of just stopping suddenly, it will slow your collision down over time, and so you will decelerate over a large amount of time, and so you'll come to a stop over a large amount of time. Even though your change of momentum will be whatever it will be, the time over which you stop will be larger, and so the force you feel is a lot less. Okay, so that's been Impact Forces. I've been Mr. Baker, and I will see you next time.